Hello everyone, my name is Ngo, and I'm working in Chalmers University of Technology in Sweden. And I'm going to present to you a work on the joint constellation design for the non-coherent MIMO multiple access channel. And this is a joint work with Sheng Yang from Southern Super Lake, France, and Maxime Guillaud and Alexis Decurninge from Huawei Technologies, France. So this is the outline of my talk. I will first give some background on non-coherent constellation design from the point-to-point channel to the multiple access channel. And then I will present our proposed constellation design criteria for the multiple access channel. After that, I will show some numerical results, and then I will conclude the talk. So in MIMO wireless communication system, the channel state information is the knowledge of the fading coefficients between the transmitter antennas and the receiver antennas. And this information is important because it enables us to adapt the transmission and reception to the current fading state. So with the channel state information, we can actually do beamforming or multiplexing at the transmitter. We can also perform coherent detection at the receiver. However, there is no free lunch because the knowledge of the channel state information is not given for free in advance. It has to be estimated. Typically, we have to transmit some Guillaud symbols to estimate it. Now, these Guillaud symbols do not carry information to the receiver because they are known at the receiver, but they do occupy some communication resources. And normally, there is some channel estimation error that is harmful because it reduces the channel throughput and increase the detection error. Moreover, in some cases, even assigning orthogonal Guillaud sequences to all the users in the system is infeasible. So to stand from a more general and more practical point of view, we would like to consider the assumption that the channel state information is unknown a priori. And with this, it is called a non-coherent communication. So for a non-coherent point-to-point channel, so let's say we have M transmit antennas and N receive antennas, and the channel output is given in this way. Here we assume that the channel is Rayleigh block fading, so the channel matrix follows a Gaussian distribution. It remains constant within each coherence block of length t, where t is called the coherence time. We assume that the noise is Gaussian with a fixed variance, and we consider average power constraint. And it has been shown that actually for this channel, in the high SNR regime, the optimal signaling is called the unitary spacetime modulation. So that is to say the input matrix ICE, it has a form of the truncated unitary matrix. And this is also called the Grassmannian signaling. So basically with this signaling, we embed the information in the subspace of the signal. And based on that, the constellation design problem for the point-to-point channel has been well studied. So we know that we should, for this channel, we should jointly map the bits into the matrix ICE, which takes values from a finite discrete set of points in the Grassmannian manifold, which is the space of n-dimensional subspaces in a complex vector field. And this is called the Grassmannian constellation. And the constellation points can be represented by the points on a hyperimage sphere, as you can see here. And to optimize a Grassmannian constellation, a common design criterion is to maximize the minimal pairwise corridor distance between the constellation points. So in short, for the point-to-point non-coherent channel, the constellation design problem has been well investigated. Now, what about the bug? So here we assume that we have k users instead of one, and we can concatenate the transmitted signals into a big matrix H, and we can concatenate the channels into a matrix H. We assume that the user K has NK antennas, and the receiver has N antennas. And as for the single user case, we assume that the transmitted signal of each user is taken from a finite discrete constellation, xk, with a size of 2 to the bk. So bk here is the transmission rate in terms of the number of bits per symbol. And actually, for this case, for the multiple asset channel, we don't know an effective and simple constellation design criterion that is somehow analogous to the max-min corner distance in the point-to-point case. So in this paper, we would like to attack this problem. We would like to design the joint constellation X, which is a Cartesian product of all the individual constellations of the users for the given set of transmission rates, so that the ML detection error is minimized. So let's take a look at the ML detection error. You know, in ML detector, we would like to find a point that maximizes the likelihood of the output. And for the channel in consideration, the likelihood function can be written in this form. And the ML detection error probability is basically the probability that the detected symbol is not the one that will transmit. And our goal is to design the constellation, the joint constellation, such that the ML detection error probability is minimized. Now, this ML detection error probability can be derived in closed form, but it has a very complicated formula, which is not easy to minimize. So we need some simpler metrics to reduce the complexity of the constellation optimization. To this end, we are going to analyze the pairwise ML detection error, which is defined as the probability that the likelihood function corresponding to the transmitted symbol is smaller than the likelihood function corresponding to another symbol. And this can be expressed as the probability that the pairwise log likelihood ratio, defined in this way, is smaller than 0. We can actually show that the ratio between the ML detection error probability and the worst case pairwise ML detection error is lower and upper bounded by constants. So we can simplify this original constellation design problem by basically replacing the ML detection error by the worst case worst case pairwise ML detection error probability, and we obtain this design criterion. Now we would like to further simplify it. So to do so, we observe that in the regime of the large number of receive antennas, then the exponent of the pairwise ML detection error converges to the mean of the pairwise log likelihood ratio. So we can simplify the design metric by replacing the worst case pairwise ML detection error by the mean of the pairwise log likelihood ratio. And we would like to maximize this metric, which we refer to as the E-mean matrix. We can even further simplify this. So we can write the mean of the pairwise log likelihood ratio in terms of the sum of these terms. And we observe that the only term which can scale linearly with the power is the last term, which is given by this trace. So we decide to focus on this term. We keep only this term in the E-mean metric, and we obtain this metric, which we refer to as the D-mean metric. We note that actually this D-mean metric, it coincides with the minimum pairwise corner distance metric in the single user case. Now, so far we have obtained a quite simple metric, which is ready to be numerically optimized for the constellation. But we can also ask ourselves, can we deduce a simple construction based on the metric? And the answer is the following. So let us consider the case when all the users have the same number of antennas and they transmit at the same power. And we let us restrict ourselves to the case of Gaussian signaling. So the transmitted symbol of each user is a truncated unitary matrix. Then we can actually show that the two joint constellation points for the joint constellation are well separated in terms of the d-mean metric that we propose, if and only if each pair of individual constellation points, either from the same users or from different users, are well separated in terms of the corner distance. So this leads us to the following construction. So we first generate a single user constellation with a good corner distance property, and then we partition this constellation into k disjoint subsets, and we just we assign one subset to each user in the multiple offset channel. So actually, if the original single user constellation has a large minimum pairwise corner distance, then the resulting joint constellation for the MAC has a large value of the d-mean metric. And we call this construction the partitioning based construction. Now, the second construction that we would like to analyze is the pre-coding design that we have proposed in our previous paper. So this design is proposed for the SIMO-MAC. So all the users has a single antenna. And the idea is to start from a single user constellation in a lower dimension. And then we decode this single user constellation to obtain a constellation of a user in the MAC. So by designing a set of decoders that are specific to each user in the MAC, we obtain a set of individual constellation for the MAC. And with this design, we can actually have a very nice geometric separation, as we can see in the example on the right here. So this is the case when we have two users and coherence times is 3. And we can see that all the constellation points of the first user, which are in blue here, they belong to one subspace, and all the constellation points of the second user, which are the red points, they belong to another subspace. So they are separated by this subspace structure. And we can show that actually the precoder that we have designed in this paper are very well in line with the criterion of maximizing the d-mean metric. So the better the joint constellations are separated in the geometric sense, the higher the d-mean metric is. So far we have proposed some design criterion and we also propose some constructions. Before evaluating the performance of our proposals, we would like to provide some baseline schemes and metrics. The first obvious baseline scheme is the Guillaud-based scheme, in which each user first transmits some Guillaud symbols, which are orthogonal across the users, and then they transmit some QAM data symbols. To design the joint constellation, there are some baseline metrics. So we can treat the joint constellation as a single constellation by considering all the users as one user with multiple transmit antennas equal to total transmit antennas of all the users. And we can adopt the single user criteria to design the constellation. The first single user criterion that we can adopt is the maximum corner distance that we have mentioned. So in this case, we would like to minimize this metric, which we call the M1 metric. Another single user criterion that we can adopt is the criterion is proposed in this paper, and we refer to this metric as M2, and also we would like to minimize this metric. So now let us compare the performance of our proposed schemes with the baseline schemes and metrics. So we consider the setting with 3 users with a single antenna each. The number of receive antennas is 4, and the coherence time is also 4. And we assume that each user has 8 symbols of the constellation. So here we first show in the red curve the performance of the constellation that is optimized using the d-mean metric that we proposed. So in the left, we show the symbol error weight versus SNR with the ML detector for this constellation, you see that it achieves quite a good performance. And on the right, we show the value of our matrix, E mean and D mean evaluated for this constellation. We see that the values of the D mean metric, which are given by the markers, are very close to the E mean metric, especially in the high SNR regime. So this confirms that we can use the D mean metric to optimize the constellation. Now, the blue curves shows the performance of the constructions that we proposed. So the pre-coding design achieves quite a good performance. Although it is suboptimal to the constellation optimized with the D-mean metric. And we see that the values of the matrix for this constellation is also lower than the matrix for the constellation obtained by maximizing D-mean. The partitioning design is working not as good, and also the values of the matrix for the partitioning design is quite low. Now we compare this with the Guillaud-based scheme. So for the Guillaud-based schemes, we see that it is working quite well. It is just slightly suboptimal to our optimized constellation according to the mean metric. We see that the value of the matrix evaluated for the Guillaud-based scheme is only slightly lower than our optimized constellation. Finally, we show the performance of the constellations optimized with the baseline metrics. We show the M1 metric and M2 metric. We see that the performance are not so good, and also the values of the metrics evaluated for these constellations, they have very similar behavior as the simple error rate performance. So we have two conclusions here. First of all, we can use our proposed metric, the mean, to optimize the constellation, which has the best performance among all the schemes that we consider here. And second, our metrics are actually meaningful to evaluate the performance of constellations, because we see that the values of these metrics are very relevant to the performance in terms of simple error rate. Now, what about the values of the other metrics evaluated for these constellations? So here we show the values of the M1 metric and the M2 metric. You see that, of course, the constellation that we obtained by maximizing these, by minimizing these metrics, achieve the lowest value of this metric. But the order of the values of these metrics evaluated for the other constellations, they are not relevant at all to the order of the simple error rate performance. So these metrics are not so meaningful. So in conclusion, non-coherent communications is a case when we assume that no channel set information is known in advance. And for this case, the constellation design problem has been well investigated for the point-to-point channel, but it has not been well studied for the multiple offset channel. In this paper, we studied the joint constellation design for the multiple offset channel in order to minimize the joint ML detection error. We have proposed a simplified metric, which is given here, which can be used to optimize the constellation. We also propose a partitioning-based construction, and we numerically optimize the joint constellation using our metric for the SIMO mark, and we shows that the proposed metric is actually meaningful for the constellation optimization and evaluation. So that concludes my talk. Thank you for your attention. If you have any question, please give me in the Q&A, or you can also send me an email to this address. Thank you.